Hey everyone, welcome back for another deep dive here on the Deep Dive. We love to help you get a grip on complex topics fast, and today we're tackling radial basis function networks, RBF networks.
RBFs.
If you've been with us before, you might remember we dove into those multi-layered feed-forward neural networks. Well, RBF networks operate on some pretty different principles, and all the insights we're bringing you today come straight from a dedicated chapter on, you guessed it, RBF networks.
Straight from the source.
So consider this your express lane to understanding this very unique type of neural network.
Exactly. And for you listening in, our goal today is crystal clear. We're going to break down these RBF networks, understand their key characteristics, what makes them tick, why they're cool.
What makes them stand out?
Exactly. And we'll explore some of their interesting variations, all grounded in the expert knowledge from this chapter, of course. Think of it as your shortcut to getting a handle on this unusual kind of neural network.
All right, so let's start with the fundamental architecture. First things first, RDF networks. They are feed-forward, meaning information flows in one direction.
Right.
But unlike those deep, multi-layered networks we've discussed, a typical RBF network boasts just a single hidden layer, just one.
One and done.
And this layer, it behaves in a very specific way, dictated by what are known as radial basis functions, hence the name.
The heart of the matter.
Now, it's crucial to note how the output gets generated. In many RBF networks, the output layer is simply a linear combination of the activations coming from that single hidden layer.
Right.
This is a pretty stark contrast to other feed-forward networks, which can have multiple hidden layers, each with their own potentially complex activation functions. Here, the relationship is usually much more direct. The input layer, as you might imagine, acts as a conduit, simply passing those input signals along to that all-important hidden layer.
Right to the action.
So this hidden layer, this is where the real magic happens. What exactly is its role in processing the data?
So what's fascinating here is how the hidden layer transforms the incoming data. The goal is often to map that data into a new space, often of higher dimensionality, sometimes way more dimensions than the original input space. And the key idea is that in this new space, the different classes or categories within our data, they might become linearly separable even if they weren't in that original input space.
So linearly separable, that's crucial for classification, right?
Yeah.
The ability to separate the data with a simple line or hyperplane.
Exactly. And this transformation relies on the concept of prototype vectors, or sometimes called centers, within that hidden layer. Think of them as like representative examples or focal points for different regions of the input space. The computation within each hidden unit, it's not based on weighted sums like in those traditional neurons, but instead it's based on how similar the current input vector is to these stored prototype vectors. So the network's behavior is very much influenced by the nature of the specific input it's processing and how it relates to these prototypes. It's like each hidden unit is saying, hey, this new input, it looks a lot like this prototype I already know.
Yeah, that makes sense. Now, the chapter delves into the math behind this, right? It gives us equation 5.1, describing the activation of the J-Douth hidden unit. The equation H subscript J of X equals.
Right, it's got that exponential term.
Yeah, e to the power of, bunch of stuff. Looks a bit technical, but let's break it down so everyone's on the same page.
Yeah, absolutely. Let's unpack it.
So we have this equation, H subscript J of X equals E to the power of negative, the norm of X minus mu subscript J squared, all that divided by 2 sigma subscript J squared.
All right, let's take it piece by piece.
Perfect.
First, we've got X, that's just our input training vector, the data point we're feeding to the network. Then we have mu subscript J, and that's our prototype vector or center associated specifically with that Jth hidden unit we're looking at. And then there's that term with the double bars.
The norm, right?
Right. It's the norm of X minus mu subscript J squared. And what that really is, it's the squared Euclidean distance between that input vector and the prototype vector. Essentially, it's a measure of how far apart they are in that input space.
And that brings us to sigma subscript J squared. What does that control?
That, my friend, controls the width or sphere of influence of the Jth basis function. Think of it as how sensitive that particular hidden unit is to inputs that are near its prototype. A larger sigma subscript J squared means a wider influence, so even inputs that are somewhat farther away will still produce a meaningful activation. Conversely, a smaller sigma subscript J squared means a very narrow, localized influence. It's like a radius of influence around that prototype.
I see. So the greater the distance, the lower the activation.
Exactly, because of that negative sign up in the exponent. So when the input X is very close to the prototype mu subscript J, that distance becomes small, the exponent gets close to 0, and e to the 0 is 1, giving us a high activation. This is really the essence of the radial nature. The activation depends on the radial distance from the center, the prototype.
Got it. It's all about distance. Now, after the hidden layer does its thing, we arrive at the output layer. The chapter presents an equation for the network output. Y, it's after figure 5.1. It's y of x equals the sum of w subscript I times phi subscript I of x, all that, plus w subscript 0. Let's break this one down too.
Absolutely. Here, phi subscript I of x represents the activation of the ith hidden unit. Note the use of the general phi symbol here, just emphasizing that it's the output of the hidden layer. The w subscript I terms, those are the weights connecting each of these hidden units to the output layer. These weights, they determine how much influence each hidden unit's activation has on the final output. And finally, W subscript 0, that's a bias term, a constant value that can shift the output.
So the output Y is essentially a weighted sum of all those hidden unit activations plus that bias. It's a linear combination, just like you said earlier. Okay, we're starting to see the structure. What are some of the key characteristics and advantages that emerge from this unique setup? Why would someone choose an RBF network?
Well, one of the most significant capabilities is the ability of RBF networks to learn really complex nonlinear mappings between the input and the output. That hidden layer transformation allows them to model intricate relationships that linear models simply can't capture. Imagine trying to classify data that's all swirled up in a spiral shape. A linear model would struggle, but an RBF network, it can learn the shape of that spiral.
And how do we actually get these networks to learn? What does training involve?
So training typically involves a two-stage process. First, we need to determine the parameters of that hidden layer, that is, those prototype vectors, the mu subscript j's, and their widths, the sigmas.
Right.
Then, once those are set, we need to figure out the optimal weights, the W subscript i's that connect the hidden layer to the output layer. It's like setting up the examples the network's going to use as reference points and then fine-tuning how much each one matters for the final decision.
So how do we choose those crucial prototype vectors in the first place?
Well, the chapter outlines a few common approaches. One straightforward method is simply randomly selecting a subset of the training data points to serve as our prototypes. Another, more sophisticated technique involves using clustering algorithms, like k-means clustering, to identify natural groupings within the training data and then using the centers of those clusters as the prototypes. The idea is that these centers represent the different categories or important regions in our data.
That makes sense, using represented data points or cluster centers. What about setting the bandwidth, that sigma value? That seems pretty important too.
It is, absolutely. The bandwidth essentially governs how localized each radial basis function is. If it's too small, each hidden unit will only respond to a very narrow region of the input space, which could lead to a very complex model that overfits the training data.
Let's try and memorize the training data.
Exactly. And if it's too large, the hidden units might activate too broadly, and the network might not be able to learn fine details.
Yeah.
It's like having a magnifying glass with a very precise focus or a much more general one.
So it's a balancing act. Are there any rules of thumb for setting sigma?
Yeah, there are a couple of heuristics mentioned. One is to set sigma proportional to the average distance to the nearest neighbors of a prototype. This tries to capture the local density of the data around each center. The chapter even gives us a handy rule of thumb. Sigma equals d subscript max divided by the square root of 2 meter, where d subscript max is the maximum distance between any two chosen prototypes and m is the number of prototypes.
Okay.
Another common choice is to set the bandwidth such that the, let's say, p nearest neighbor of each prototype is equal to its PA nearest neighbor, leading to sigma equals d subscript avg divided by the square root of m times p, where d subscript avg is the average distance to the p nearest neighbor.
So these give us starting points for tuning this crucial hyperparameter.
Exactly.
Okay, so we've got our prototypes, we've got our bandwidth set. Now, how do we actually learn those output layer weights?
Well, once the hidden layer parameters are fixed, the problem of finding the optimal output layer weights becomes a linear problem. Since the output is a linear combination of those hidden layer activations, we can use linear regression techniques to learn these weights. This often involves minimizing a sum of squares error function between the network's predictions and the true target values in the training data.
Okay.
It's a relatively straightforward linear optimization problem to solve.
Now, the chapter also mentions regularization. Why is that important in the context of RBF networks?
So regularization, it's a crucial technique to prevent overfitting, especially when our model has a lot of parameters, which can happen with RBF networks, particularly if we have a large number of hidden units. Equation 5.2, it introduces a common form of a regularized error function.
Right. L equals 1/2 the norm of HW transpose minus y squared plus lambda over 2 times the norm of W squared. Okay, let's unpack that. We've got the first part, the 1/2 times the norm squared stuff. That looks like our standard sum of squares error, the difference between the network output and the target output.
Yeah, that's the core error term.
Okay, so what's that second term doing?
The second term, that's our regularization term. Here, W represents the matrix of output weights, and the norm of W squared, it's essentially the sum of the squares of those weights. The parameter lambda that controls the strength of this regularization. By adding this term to our error function, we're penalizing large weight values during training. It's like putting a constraint on the weights to keep them from blowing up.
So it discourages the network from relying too heavily on any single hidden unit or having excessively large weights, which can be a sign of overfitting. It's a way to keep the model more generalizable.
Precisely. And this regularization, it leads to a closed-form solution for the optimal weight vector, as shown in equation 5.4.
Right.
Which is quite convenient because we can directly compute the optimal weights without needing any iterative optimization algorithms.
Now, RBF networks aren't just one monolithic thing, right? The chapter mentions variations and special cases. What are some of the interesting twists on the basic RBF network?
Absolutely. The chapter touches on several variations. One example is the orthogonal least squares algorithm. It provides a more structured way of selecting those prototype vectors. Instead of random selection or clustering, it iteratively adds prototypes based on their contribution to reducing the error. Then there's the concept of fully supervised learning for training RBF networks, where, unlike the two-stage approach we initially discussed, the hidden layer parameters, the prototypes and widths, and the output layer weights are learned simultaneously using gradient-based optimization. This allows for a finer adaptation of all parameters.
That sounds more integrated. What about using RBS networks for classification tasks specifically?
Right, so the chapter introduces modifications like the classification with perceptron criterion, that's equation 5.9, and the classification with hinge loss, equation 5.11. These adaptations involve using different loss functions that are tailored specifically for classification. Instead of simply minimizing the squared error between the output and a continuous target, these loss functions focus on correctly classifying data points into discrete categories. For example, that hinge loss, it penalizes incorrect classifications, but it also penalizes classifications that aren't confident enough. It's like adjusting the objective function to be laser focused on the classification task rather than continuous value prediction.
And there's an example of linear separability promoted by RBF that the chapter mentions. What's the key takeaway there?
So what's fascinating here is that this example visually demonstrates a core strength of RBF networks for classification. It shows how data that's not linearly separable in the original input space can be transformed by that RBF hidden layer into a representation in a higher dimensional space where the classes can be separated by a simple linear decision boundary. This highlights the power of that nonlinear transformation performed by those radial basis functions. It's like the network finds a new way of looking at the data where the categories become clear.
It really brings it full circle back to that hidden layer transforming the data. Now, the chapter also delves into the relationship between RBF networks and kernel methods. That sounds like a deep connection.
It is a very close relationship indeed. RBF networks are fundamentally linked to kernel methods, particularly kernel regression and support vector machines, or SVMs, that use RBF kernels, Gaussian kernels. Think back to the activation of a hidden unit in an RBF network, that equation we talked about earlier. It has exactly the same functional form as a Gaussian kernel function centered at mu subscript j. Essentially, each hidden unit is computing a similarity measure between the input and its prototype, just like a kernel does.
So each hidden unit is essentially acting like a kernel function.
Precisely. And in kernel regression, the prediction for a new input is directly computed as a weighted sum of kernel functions evaluated between that new input and each of the training data points. Equation 5.17 gives us a glimpse of that.
Okay.
You can see the similarity to the RBF network output, where the training points themselves often serve as the centers, and we learn weights associated with each one. Kernel regression is, in a sense, an RBF network where every training point is a prototype.
And what about the connection to SVMs with RBF kernels?
So the prediction function in an SVM with an RBF kernel, equation 5.21, It also takes the form of a sum of RBF kernel functions.
Okay.
However, in SVMs, these kernel functions are centered only on the support vectors, those crucial data points that lie closest to the decision boundary. This leads to a more sparse representation compared to kernel regression or RBF networks, where all training points might be used as centers.
That makes sense.
The SVM pinpoints the most important examples for defining that decision boundary.
That's a powerful connection. It seems RBF networks sit within this broader family of kernel-based learning methods.
Yeah, it's a rich family of methods.
The chapter concludes with some observations. What are the key takeaways there?
One crucial observation revolves around the number of hidden units, or prototypes. Increasing the number of prototypes can certainly lead to an improvement in accuracy on the training data. The network can more finely tune itself to the specifics of the training set. However, this also comes with the risk of overfitting, where the network learns the noise in the training data and generalizes poorly to new, unseen data. It also increases the complexity of the model, requiring more computational resources. It's that classic trade-off between memorizing the training data and learning general patterns.
So again, it's that familiar balance between model complexity and generalization ability.
Exactly. And related to this is the importance of choosing the right number and placement of those prototypes, as well as the careful selection of the bandwidth, that sigma, for each radial basis function. These are critical design decisions that significantly impact the performance of the RBF network. There's no one-size-fits-all answer. And these hyperparameters often need to be tuned based on the specific problem and data set. Intuition and experimentation play an important role here.
Well, this has been a truly illuminating deep dive into radial basis function networks. We've covered their unique architecture, the crucial role of the hidden layer, and those radial basis functions, the math behind their activation and output, how they're trained, some interesting variations, and their deep connections to the world of kernel methods.
Indeed, to sum it all up, RBF networks offer a distinct approach to neural networks, leveraging a hidden layer of radial basis functions to learn complex nonlinear relationships. Their architecture and training process bring a different set of strengths and considerations compared to traditional deep feed-forward networks, and their strong ties to kernel methods provide a valuable theoretical foundation.
So, for you listening in, consider this. Given the remarkable ability of RBF networks to transform data into a higher dimensional space where it might become linearly separable, how could this fundamental principle of representational transformation be applied to understanding and tackling complex problems in fields that might seem very far removed from the world of machine learning? Could this inspire new ways to analyze data and uncover hidden structures across diverse domains? Definitely something to ponder.
A fascinating question to consider. Thanks for joining us on this deep dive. We encourage you to continue exploring the fascinating world of neural networks and the power of representational transformation.
Thanks for diving in with us, and we'll catch you next time.